Hi, you're welcome back. In this clip, we look at costs and all the different types of costs because we never get costs actually quantified. At the Dock Regional Technical College, they have one large turbine. It's a medium actually by today's standard. And they tell us that they got 45% of a grant for that. So assuming that's the average for the wind farms generally, that's a huge lump of taxpayers' money going into these windmills. They also get rapid depreciation. In other words, the value of it is allowed to go down in their accounts against taxation, and therefore that's a cost to the taxpayer. Private investment in wind farms is down 57% according to the Taoiseach and Kenny last April. So now we look at fixed costs. You have your wind farm up and all, and the fixed costs include payment to landowners. So in Ireland, for example, you have farmers getting so much a turbine. In Britain, it's a percentage of the actual profits. So salaries for executives and companies and all that is another example, anyone permanently working. Insurance costs and office costs. Now we look at variable costs, and one is maintenance of the turbines and the transport to get there and from. But more importantly, in my view, is hidden costs, the costs that are not quantified but are still loaded on us. So one of them is the management of wind on the grid. You have to have extra staff, and it takes extra effort to manage erratic wind on the grid. Providing firm backup generation. Now this is a huge cost considering that the conventional generators have to take all the wind that a wind farm can offer, whether they want it or not, by priority dispatch. So this is a huge cost. And the evidence now is coming that there's no reduction in conventional capacity or in the burning of fossil fuel. This is my challenge to the industry, to show me that there's any significant reduction. Hot spinning reserve. Long ago you'd have a few heavy based plants burning oil and coal, etc. And they were very efficient and very cheap. They're moving away from them now to quick-fired gas plant, which is not as efficient. Diesel engines and the hydropower, the Shannon hydropower and other hydropower is being diverted to back up wind rather than doing what it used to do, is provide reserve backup for conventional power. So you have a duplication, and that's a cost on us. None of this is borne by the wind farms. It's all loaded on us. And it is my contention that this cost is not just money, it's the fossil fuel we have to burn as well. The next point is that wind farms, you may not know this, they use a lot of wind power, a lot of grid power. They use the power from the mains power. They need that for lots of things. The old aero generators, the old things I showed you in the previous clip, they didn't need any mains power, but the modern wind farm needs a lot of it. If you look at a wind farm, you'll see that there's a three-phase line out of it, and there's also a three-phase line into it. One of those lines is to carry power into the wind farm. So among the things that is needed for is what's known as blade pitch control. That's to adjust the blade to suit the wind speeds at a particular time. They're turned around. So that's blade pitch control. The next thing is a braking system. This is a hydraulic braking system. Essential. This is operated by the grid. This takes a lot of power. The next thing is power conditioners. These make the power suitable for connection and export to the grid. And they're reckoned to use between 1% and 2%. In some cases, the power is converted from alternating current to direct current, and then it's reconverted back to alternating current using the line frequency from the input to get it into the correct phase. The next thing then is the yaw mechanism. And this is the part that fits on top with the turbine on it, and this is rotated to suit the wind by the yaw mechanism, and that's operated by an electric motor from the grid. Unwinding the cables. As the top of the turbine, the neckle, turns around, the cables they become entangled, twisted, so they have to be unwound every so often. That's done by a computer, but the energy comes from the grid. Lights. Sensors, communications, data collection and onboard computers all use grid power. Now de-icing is another very important one. If you leave a turbine in very frosty conditions, stationary, ice will build up on it, and even if it's moving. So they usually run electric elements down through them to heat them so that the frost won't build up. If the big lump of frost built up and it started, it would fling it off. So it would be dangerous. So that's another source, de-icing. Forced lubrication. In most of the big machines, the oil is pumped into the bearings by means of, just the same as your car, by a pump. And that oil has to be both pumped in, and it also has to be kept warm, because if it's thick it won't go through. That uses quite a bit of power. Now, direct current used in wound rotors is another example. And I'll just show you what I mean by that. Here is a particular type of generator. It's a wound rotor. I've already maybe alluded to it. You see there that there's two wires going in, and the magnetism in this rotor is provided by direct current. And that runs round inside in a starter like that and provides three-phase power. Okay, that's the general idea. Now, in that case then, I'll show you a little exhibit I have here. And you may have seen this in the practical demonstrations. I'll just produce it here again, and I'll put it running. Now this is a sort of a replica of a grid-powered electrical system. So I'll leave it there and get it set up. I'll just put it running. And as it starts to run, you'll see that the bulb here does not light. And if I take a battery and a small battery connected to it, you see that the bulb lights. Alright. The bulb lights up. That's a 9-volt battery. Here's a battery that's partly discharged. And the bulb light's a bit brighter. We get a fairly new battery. You see the bulb lights, and the motor slows with the extra load. See the motor is slowing with the huge load. Okay, this device is being driven by standard half horsepower electric motor. Now, I want to show then, if I switch it off, it's been suggested that using this, that you could actually feed power from the grid into the turbine when it wouldn't be running and produce power. But you see there is actually no power, and I've tested this before. No matter how much power you feed in, you will not get power, and it's sparking there. You'll not get power on the bulb. So I don't think you can recycle power. At least my tests so far indicate that you can. But once it's running, it will not go without power input. There it is. So that's just a little practical demonstration to say a picture paints 1,000 words, and we leave it over here. But that is a major hidden cost. Now, if it's not a wound rotor type machine, it may be this little device here that we've seen previously, and it may be a magnetic rotor, in which case there's cogging, you feel that. Now, in marginal wind conditions, you need a little motor like the starter of a car to keep that going. And if it's an induction motor, you also have problems. You have to keep it going using the grid. So no matter what type of generator it is, particularly in low or marginal wind conditions, if you want to avail of all the money that's been made, you need to keep your turbine going near cut-in speed, so that when the wind gives a gust, you get that little bit of power. Otherwise, it'll take a while to get it up, and you need good winds to get starting. So that's the DC motor. Now, the other one is driving the turbine in calm conditions. Sometimes they have to be driven for various reasons in calm conditions, and this is done also by using it as a motor. It's also done by the grid. Particularly in marginal winds, this happens. Preventing warping is what's here. In other words, the turbine blade may warp in hot weather, and even though it's totally calm, it's best to keep it going round. So that's taken from the grid as well. And jacking the shaft. A large shaft on a ship or anything else, a large heavy shaft, just like a piece of steel, will warp if left long enough in stationary positions. And ships in port tend to jack the shaft by keeping them going around slowly. So that's another use. Now, at a minimum, this power amounts to about 2% of total. There's no doubt at all that it's taking about 2% of the power for this, because it's very hard to get it quantified. But at a maximum, it's up to 12%. Now, I have a letter here in which I asked the minister, was there a meter on this power? And the reply is quite simple. He says the meter on a wind farm measures how much electricity is exported from the wind farm, and it does not measure what is used on site. And this is signed by the minister's agent, and it's dated April 2011. So they don't know how much this power is, and they haven't it metered. So there's no meter at all. Nor is it charged for in any way. Now they're going to make the point, and do make the point, that all generators use their own power to some extent. But these wind farms have to use this grid power. These have been put up to stop using grid power, which is more, they don't own the power that's been produced. The ESB, if they produce power, they have to set a bit aside, and that's added to the cost of sales. In this case, you could be doing nothing on wind, and like electricity, you could have a lot of wind power, and they're credited with producing green energy. But they don't tell us that they're drawing this power free from other producers and from the general pool. And this is another more of this spin that we're getting. So all this power is not charged for. And when you consider that we've already discovered that the contribution wind farms make is very little, well, when you take this from it, then it could be worse. Now, parasitic means a thing that's harmful, like ticks on a cow, let's say, and symbiotic means they're beneficial. That's like a bird picking a crocodile's teeth. So I maintain that these machines are parasitic. They live off the wind farm. They live off our electrical system. They are not beneficial to it. They're just passengers, really. Whereas other people say no, that they can be symbiotic. They can have a benefit at times. I'd like someone to show me what those benefits are. It is my estimation that the power, the energy used, or the electricity being used by today's wind farms, at 21% of wind, is what would power the town of Drogheda in County Louth. Now, the only sure and safe way, and the only just way to pay for this energy, is to take the net power of the wind farm exported and take from it the power that's fed in. In other words, to meter the input and the output and only pay for the difference. But of course, even that is paid on load factor, and I've shown a particular view on that. But that would be at least a bit fairer, and it would stop the wind companies and all these getting paid for wind power, which actually has an element of grid power in it. Because if it needs grid power to use it, then it's not really green. This is the point about it. Now, the department don't know if there's any saving. I have that there in a letter, and they don't know if there's any saving from emissions at all. We've said that already. So anyway, it's possible. It's possible when you add up everything, and looking at the evidence overall, that wind farms are net consumers of fossil fuel generated and nuclear power. Now, the way the Irish Academy of Engineers have phrased this in the report is, and they say this: the costs of wind farms are loaded onto the backs of already hard-pressed consumers. So I couldn't say it better myself. And in that now we see that there is a huge hidden cost in wind farming that is being kept from us, and that it should be accounted for, and they should be made pay for it. And if they were made pay for all that and taking everything into account, there'd be no wind farms. So that's it. We'll see you back for clip 4 and on subsidies when you have time, and I hope you enjoyed that. Thank you.